Very good. I'll begin. This is Lecture 9, which is on isomorphism and Cayley's theorem. I have a bunch of examples that I've worked out this afternoon that I think you'll appreciate that add a lot of depth to this lecture that's not here in the notes as it currently stand. But anyway, what's in the notes is good. Some of it we've actually talked about before. The first result here in Lecture 9, concerning isomorphism gives equivalence relation. This is old news for us. So here we have two isomorphisms, one from G1 to G2, the other one from G2 to G3. This proposition states that the identity map is an isomorphism, that the inverse of an isomorphism is an isomorphism, and that the composite of an isomorphism is an isomorphism. And so these things, it'd be wise for you to work through this. Those are pretty good test questions. They're not that hard if you just understand what's being asked. I allow us to use, for example, Math 200. Math 200 tells us that the inverse of a bijection is a bijection. So what I'm saying here in this proof is that the part that matters to us is the structure-preserving part. So I focus on showing the homomorphism property for the inverse in this argument. And likewise for the composite, I focus on the homomorphism property because the fact that the composite of bijections is a bijection, or that the inverse of a bijection is a bijection, is already known to us from a prerequisite course, okay? All right. Now, it may or may not be known to you. That's, it's okay. Well, what am I saying? No, it's not okay. But you don't have to show that part, okay? I'd be happy to talk to you about why it's true in office hours, though, if you want. Now, one of the other things that the proposition above gives us is that we have that, as I've mentioned this before, but isomorphism of groups is an equivalence relation on all groups, right? Because any group is equivalent to itself under the identity. If you have, an isomorphism from G to H, then the inverse of that map is also an isomorphism from H to G. So we've got symmetry of isomorphism, we've got reflexiveness of isomorphism of groups, and also we have transitivity of isomorphisms of group from part 3 of the proposition above. In other words, isomorphism is an equivalence relation on groups. All right. And so roughly speaking, two groups that are isomorphic are essentially the same group up to notation, as I've been trying to sell to you for the last couple weeks. Now, in this lecture, we're going to look at some special kinds of group isomorphisms. And the first kind of those is just generically what's called an automorphism. An automorphism of a group is simply an isomorphism from the group to itself. I also use this language in linear algebra if you had it with me. You may have forgotten, but we did use it there. So in linear algebra, an automorphism of a vector space is a linear transformation from the vector space to itself. So, which is also an isomorphism. So it's an invertible map from V to V would be an automorphism V, where of course we assume linear map there because we're talking about vector spaces. But anyway, let me get back to the group theory. Recall we've also talked about permutations on a set. That's a set of all bijections on the set, right? So permutations does not assume structure preserving. It's just a bijection. Isomorphism is more than that. It's a bijection which is also structure preserving, so it makes sense that automorphisms would be a subset of permutations. And in fact, we can argue that the automorphisms of G, in fact, form a subgroup of the permutations of G. And so if we have, for example, if we have phi and psi in the automorphisms, then the composite phi with psi inverse is a mapping from G to G, which is again an automorphism by the proposition at the start of this section, right? Because the composite, well, first of all, the inverse of an isomorphism is an isomorphism, and the composite of isomorphisms is an isomorphism. So this is an isomorphism from G to G, which makes it an automorphism. So then I've noted that the identity's in there, and that the composite with the inverse, this is in there. So by the one-step subgroup test, we have that the automorphisms of G is a subgroup of the permutations of G. Then, I next move on to talk about conjugation. Conjugation by G, the conjugation map, phi of G of x is gx G inverse. Well, this is conjugation by G. You could just as well do G inverse xg, and I probably will do that at some point by accident, but for the moment, let us define phi sub g to be that, all right? And I'm going to keep using this notation throughout the remainder of this lecture. So you can show, and I say the footnote actually has the details of why these things are true. But it turns out that phi e is the identity on G. Phi sub gh is phi g composed of phi h, and phi g inverse is in fact phi g inverse. Curses upon you, English. So it follows that if you were to look at the subgroup of automorphisms that were formed by conjugation maps, that is itself a subgroup of the automorphisms of G, which may be a proper subgroup or maybe the whole of the automorphisms of the group. It kind of depends on the nature of the group. Say we covered the example, page 121 to 122 in class. I think I said that you could look at 2017 lectures, but maybe that's even 2016 lectures. I'm not sure what year that's from. This may be a relic of when I used Galilean last time, the first time I taught this. I don't know, guys. Sorry about that. By the way, the footnote I was mentioning is down here. See, phi of gh of x is gh x gh inverse, but then by sock shoes, that and associativity, that's gh x h inverse g inverse, and then in the inside that's phi h of x, and then that is phi g of phi h of x. And since that's true for each x and g, that shows you that phi of gh is equal to phi g composed with phi h. And then the other things that I claimed in that example we're just looking at follow through very similar calculations. All right. But we have a definition that I should share with you, which is that if we have an automorphism, in other words, an isomorphism from G to itself, and that automorphism can be written as conjugation, then it's called an inner automorphism. In fact, the set of all inner automorphisms is denoted in G. And so we have this nesting of subgroups. We have the inner automorphisms, are a subgroup of the automorphisms, are a subgroup of the permutations. And generally, these are equalities not met anywhere here, but it could be sometimes. Now, this example 2.95 I was selling to you as a nice sort of starting point to understand your homework, which is to prove the theorem, which is on the next page. And essentially, this is to look at to understand what are the automorphisms of Z3, which is the set 0, 1, 2. So if you look at Z3, we have generators 1 and 2, right? And remember that isomorphisms must map generators to generators, right? So if you think about it, if we look at 1, we can either send it to 1, or we can send it to 2. And I'm suggesting that alpha sub 1 is the map that sends 1 to 1, and alpha sub 2 is the map that sends 1 to 2. And if you look at it then, alpha 1 of k is by definition, not by the definition, but by the, how to say this? By properties of homomorphism, that's phi 1 of 1 added together k times, or it's that. I mean, anyway, I guess I'm re-deriving that identity again here, but whatever. The point is that phi 1 of k works out to k. Since that's true for all k, you can see that phi 1 is just the identity map, right? On the other hand, phi of 2k is k times phi 2 of 1, which is 2k. So apparently, phi 2 of k is not the identity map, it's the multiply by 2 map in Z3. And then you can calculate the composite of phi 2, alpha 2 with itself, which you want to do. I may have said phi, I meant alpha. You want to compose the alpha with itself to understand the multiplication rule of these isomorphisms. So when I do that, I get alpha 2 of 2k, which is 2 times 2k, which is 3 plus 1 times k. Well, that's k again. So in other words, alpha 2 has order 2. It's its own inverse. And we can look at the following Cayley table for the automorphisms of Z3. I know that there are just 2 because there are only 2 generators, so there's only 2 places to send 1. If you think about it, you can count the number of possible automorphisms by the way you have to assign generators. And because 1 generates everything, you can prove that each automorphism in this context is completely fixed by what it does to 1. So if you think about it, well, if I say much more, I'm going to solve your homework problems. I'm going to stop. But anyway, for Z3, we've got alpha 1 and alpha 2. Alpha 1 is the identity, and alpha 2 times alpha 2 is also the identity. And you can see that that's isomorphic to U3, which is this. These Cayley tables have the same pattern. And it's not hard to see that the explicit isomorphism is phi of alpha j equals to j in my current notation. This discussion can be generalized to your homework problem. So I'll let you do that. It is, after all, your homework. So, yes, as advertised on the next page, automorphisms. And the group of units for Zn are isomorphic. Zn is isomorphic to Un. I enjoy that homework problem a lot. That's a fun one. It is. It seems scarier on the face of it than like the one we had in the last homework, where the the order of AB, where A and B commute, and the order of A and B are relatively prime. Then we have that the order of AB is order of A times order of B. That seems like it might be easier, but to me that problem is way harder than this one. Anyway. All right, moving on. Are there, are all the automorphisms inner automorphisms for Zn? Well, I don't know. Let's see here. When a group is not cyclic, well, this is the question I'm asking. Here's what I say. When a group is not cyclic, but we have generators and relations for the presentation of group, it may be still relatively easy to calculate inner automorphism. So if you're wondering what this example is, basically I'm calculating, I define a particular phi. I say let phi be the map that maps x to x and maps y to x squared y. All right. It's got to do something like that because it has to send generators to generators. So here I'm just sending the x to itself, which means it's a generator of the same type. I'm sending y to x squared y. This has order 2. That also has order 2. So this defines a possible, it may define an isomorphism. Just because you send generators to generators doesn't make it an isomorphism. You also have to comply with the other structure of the group. But at a minimum, we must maintain the order of images under an isomorphism. Just because you send generators to generators, though, that doesn't make it an isomorphism necessarily. You also have to preserve the relations for the group. Anyway, that aside, this particular phi can be shown to be, what I'm showing here is that when you look at the action of this map phi on x to the m, or x to the m times y, it equals the same thing as conjugation by x on x to the m, or conjugation by x on x to the my. And so the mapping phi and the mapping phi sub x, they are equal on every possible input from D3, which means that they're equal as functions, right? And that means then that phi is in the inner automorphisms of D3 because I've just shown through this argument that is in fact a conjugation map. Now, there are doubtless easier ways to do it, but that's just a sample calculation, all right? So then that brings us to the next part of this lecture, which is kind of a little bit different. It's what's known as Cayley's theorem. And so Cayley's theorem concerns a rather well-known result, which is that every group can be looked at as a subgroup of it can be represented faithfully by some subgroup of permutations on G. Now, oopsie. There's an important bit of fine print here. I believe well, at least I'm worried about G being infinite. Maybe I don't need to, I don't know. Let's just look at the proof and see if we think G could be infinite and this still makes sense. I mean, we can talk about permutations on an infinite group just the same, that's true. But I would say that some of the examples I'm going to show after this theorem might be harder to hack for an infinite group, or maybe not hackable at all, I don't know. So the claim is that if G is a group, then we can find an isomorphic copy of G in the permutations on G. The way I'm going to do that is to say that the permutations, which are isomorphic copy, are the left multiplication maps. So here, if the identity is a bijection, great. We can define left multiplication by G by L sub G of x as Gx, all right? And so if we have G and H in G and X is another point in G, by associativity of multiplication, we can look at the composite L composed with H L sub g composed with L sub h of x, that would be GHX, which will be GHX, which will be L sub GH of x, right? But that holds for all x, which shows you that this formula holds for left multiplication maps, right? L sub g composed with L sub h is L sub GH. And by the same calculation, essentially, we have that L sub g composed with L sub g inverse is L of GG inverse, which is L of E, but multiplication by the identity is the identity map. So this shows you that if we'd say G bar is the set of left multiplication by G maps in G, well, this is a subgroup, right? This is in fact a subgroup. I'm arguing that this is in fact a subgroup of permutations on G because it's a set of bijections, right? I just showed in the step above that G has an inverse, L sub G inverse, and I showed that the composite of them was one of them again. So, and I showed the identities in it again, right? So by the two-step subgroup test, I have already proved that G bar is a subgroup of the permutations of G. And what I'd like to argue is that G bar is in fact isomorphic to G. And so here's the isomorphism I'm proposing. Let phi go from G to G bar be defined by simply map G to its left multiplication map. So by construction, LG is into, in other words, it is actually assigning a permutation, not just a permutation, something in G bar. And we also have structure preserving because phi of f composed with G is L of f composed with G, which is, LF composed with LG, which is phi of f composed with phi of G, thus phi is a homomorphism. And it's also surjection because each thing in G bar has phi of f is equal to L sub f, right? That was kind of not surprising. And let's see here, finally, if I have phi of G equals to LG equals to the identity, that implies that LG of x is equal to the identity of x, which means that G is equal to E. So what I'm proving here is that this mapping phi is in fact, it has kernel the identity, which proves that phi is injective. So it's surjective, it's injective, it's structure preserving. In fact, it's an isomorphism. I don't believe anything here requires finiteness of the group. So there you go. But of course, permutations that we're most familiar with, the symmetric group on N, well, that's going to require what I'm trying to say is if your group is infinite, you can't represent it with a subgroup of a finite group, okay? That would just violate basic tenets of cardinality. You can't have a one-to-one bijection. You have a bijection between an infinite group and a finite group, right? Is no allowed. All right. Anyway, this is called the regular representation of G on permutations. All right, so I have some examples which kind of show you, maybe make a connection, if you will, between this theorem that I just, proved kind of dry, maybe a little bit scary, I don't know, theorem about left multiplication maps, and what I'm going to do here is just look at the Klein 4 group and how that, trying to find the right zoom here, that was an issue. Trying to find the right way of looking at Cayley's theorem. All right, I'm going to show you how Cayley's theorem is fleshed out in detail for the Klein 4 group, okay? So let's start with some pictures. Basically, each one of these represents the possible left multiplications in the group. So this picture, I'm saying I start with the identity in the Klein 4 group, and then I left multiply by A. And just here, I'll write it out up here. Let me write it in a different color. So just to be dumb about it, LA of E is equal to AE is equal to A. That is how I get from here over to there. All right? And then I multiply by A again, and LA of A is A squared, but A squared is the identity in the Klein 4 group, and so I got this little picture. E goes to A goes to E. Now if I start, and then what I do to complete my picture time here is to pick something that I haven't already hit. So I've got E, I got A, but I haven't hit B yet, right? So I go to B, Left multiply by a, go to ab. Great. Then if I left multiply by a again, then I get aab, which is a squared b, which is just b again, so I've closed the loop. And once I've covered all four things, I know I'm done. So you maybe can already anticipate this is like a 2-cycle, this is like a 2-cycle. The identity just, you know, loops everything back to itself. It's kind of a, you don't even really need to draw this picture. I just drew it to be, I don't know, magnanimous, I guess. Whatever you want to call me. You can call me whatever name you want. E, LB goes to B, and multiply by LB again, we get B squared, which is E, likewise. So start with A, go to BA, which is AB, because it commutes in the Klein 4 group. Multiply by B again, we get B squared A, which is A again, so great. And then you got the AB, left multiplication by AB, which goes, takes E, moves it to AB, moves it back to E again, and A maps to, well, like, if I map A by LAB, I get ABB, which is AB squared, which is A, which is why I got that picture. Great. Now, one way we could think about this is to generalize our notion of cycle notation, and we could do something like this. The identity is epsilon. Left multiplication by A is literally equal to the composition of this cycle and that cycle, meaning that AB maps to B and B maps to AB, right? And E maps to A maps to E. Like, just a straightforward generalization of the cycle notation, but I got to put some commas in, otherwise it doesn't quite make sense. Technically speaking, if you really think about it, we probably had to put some commas back in our other cycle notation. We just don't appreciate it because we typically work with S sub n with n less than 10. So the issue of the commas is less obvious. But just saying. Anyway, this would be the EB cycle and then the AB cycle. This has got your EAB cycle and your AB cycle. Now, this, great, lovely. That's a notation we could adapt. I mean, this comma this, comma this, comma this is literally this set of left multiplications on the Klein 4 group. Now that's not the isomorphic. That's actually, okay, so fine, you got me. That actually is the G-bar. These blue things taken together form the G-bar in the group. But actually, what we like to do when we implement Cayley's theorem is to go a step further and use yet another isomorphism to, instead of looking at G, like, think about labeling G. So think about labeling G, excuse me, you know, like, this is number 1, this is number 2, this is number 3, this is number 4. And so if I think about those, you know, as group members 1, 2, 3, and 4, then that suggests the following isomorphism. I map the identity, the left multiplication map by E to the 1. I map this to the 1, 2, 3, 4 cycle in S4. I map this to the 1, 3, 2, 4 cycle. I map this to the 1, 4, 2, 3 cycle. Now this is very natural. E is 1, AB is 4. That's why I got 1, 4. A is 2. B is the third one, so that's I got 2, 3. So basically, instead of using the labels of the Klein 4 group that we usually do, we relabel the elements in the Klein 4 group. We enumerate them 1, 2, 3, 4, and then we just use plain old garden variety cycle notation. And in fact, this mapping is an isomorphism of the G bar into a literal subgroup of S4. In fact, the Klein 4 group is isomorphic to this literal subgroup of S4. All right. So this is a subgroup of S4 which represents K. In fact, it represents it faithfully. It has everything that K has, and it's a subgroup of permutations on 4 numbers. So there you go. All right, that's my first example. Won't be my last. I don't know if I've actually asked you guys any homework on this stuff this time, but I probably should have. Now, next up, and I will try to scan these and post them for you, of course, all right? Assuming my scanner works, which of course is assuming, well, sometimes that's assuming too much. Hopefully, just hope for the best. Maybe, hopefully the hurricane hasn't knocked it out yet. Let's see here, you never know. All right. So this is the Quaternion 8 group, which we have not had the pleasure of discussing before, I don't think, but it is an 8-element group formed by plus or minus 1, plus or minus I, plus or minus j, plus or minus k. sometimes called the versors. And I'm enumerating the group. You know why, maybe? And here's the rules. I times j is minus j times I is k times I is minus ik is j times k is minus kj is I, and I squared equals j squared equals k squared equals minus 1. So this is a particular subgroup of the quaternionic 8 group. Well, the quaternions, actually. So it's a finite dimensional subgroup of the infinite dimensional quaternion group. Well, not quaternion group, but the quaternions. Quaternions form an algebra. More on that later. And here's some pictures. So if I look at left multiplication by minus 1, it takes 1 into minus 1. It takes I to minus I. It takes j to minus j. It takes k to minus k. Left multiplication by minus 1 just creates these like 2 cycles. Bop, 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 bop. Left multiplication by I, on the other hand, is more exciting because it maps 1 to I. It maps, just like with a cycle calculation, you can start out wherever you want. These pictures, you can start out wherever you want. You just got to make sure you cover everything. And you should find that things loop back to where they started. I mean, that's going to happen. Anyway, so 1 maps to I maps to minus 1, minus 1 maps to minus I, and then minus I times I is minus I squared, which is 1 again, so we're back where we started. We got a 4 cycle. Now, if we start with j, it's more exciting. So j maps to ij, which is k, which maps to ik, which is minus j, which maps to minus ij, which is minus k, which maps to minus ik, which is j, way back where we started, another 4 cycle. On the other hand, we could look at left multiplication. I'm only going to do 3 of these. There's 8 of these pictures to do, right? I just got tired after 3. Left multiplication by j. Well, go from 1 to j to minus 1 to minus j back to 1 again. On the other hand, if you start at I, you go from I to minus k to minus I to k to I again. So there's these 2 4 cycles. In the generalized cycle notation, this would be literally, in my sneaky notation, which is, I don't think just mine. I forget where else I've seen this, but I feel like it must be my brother's fault. Anyway, here you go. These are 3 explicit elements in the quote-unquote G-bar of the theorem. These are literal left multiplications on the quaternion 8 group. With the nomenclature introduced in green above the quaternion 8 group, we have the following corresponding cycles in S8. The 1, 2, 3, 4, 5, 6, 7, 8, like so. We have 1, 3, 2, 4, 5, 7, 6, 8, and we've got our 1, 5, 2, 6, 3, 8, 4, 7. And if you're wondering, it's because, okay, so like, let's go through it. This is 1, j is 5, minus 1 is 2, see? And then minus j is 6, that's why I have 1, 5, 2, 6. And then this one starts at I, which is 3, and then we go to minus k is 8, then we go to minus I, which is 4, then we go to, where was I, k, which is, oh, I'm wrong, lost my place. No. Oh man, where was I? What was I? Oh, minus I, which was 4, and then we go to k, which is 7. I was thinking k was 8 for a second there, which is just wrong. K is 7 in my nomenclature. All right. Anyway, so here you go. You can define an isomorphism from the quaternion 8 group to the symmetric group on 4 symbols, 1, 2, 3, 4, and it is defined by this goes to that, that goes to that, that goes to that, and there are 5 other rules which I don't care to derive right now, but I hope that gives you a sense of how you do these. All right, so let's move along. So similar, the thought process here is very, very similar. I mean, you can find permutations wherever you look. I'm giving you a sense of how that's done in this little lecture here. So we've also talked about symmetries of a plane figure. The symmetry is the set of isometries which fixes the plane figure. So, so here's what that looks like. Here's a picture, all right, for an equilateral triangle. I want to find the symmetry group. And so what I've done is poor planning on my part. I drew these first, and then I meant to draw this above them, but you know, I drew it below, so it is what it is. It's not a bad picture, it's just not what I originally intended. So if I look at the 1, 2, 1, 2, 3, which is just how I numbered them, don't ask me why. I sometimes number them clockwise, I sometimes number them counterclockwise. Don't try to read anything into it, it's just my choice on a given day, okay? Anyway, so 1, 2, 3, if I do the identity, it just maps to 1, 2, 3. If I rotate by 60 degrees about the center, I go to 3, 1, 2. I'll read from the top. If I rotate again, I go 2, 3, 1, right? Now these are all red because if you imagine this being a literal little triangle, these rotations keep the top side up. But you can also talk about reflections, like, you know, flip over the, I usually draw a little to give you a sense of the axis of the flip. So the reflection is across the vertical axis, 1 is fixed, the 2 and 3 are moved. And then if you rotate that thing, you get to RF, which is this. So rotate means I counterclockwise 60 degrees, which is going to take that 1 and move it down there. Take this 2 and move it up there. Take that 3 and move it over there, like so. And you can even see in this picture that if we first flip and then rotate, that's the same as if we do RF like this. Well, anyway, this is RF actually. And this is R squared F up here, which we could also see as doing an RF and then R again. Alright, so these are the 6 symmetries of the equilateral triangle. These involve flipping the triangle over. Strictly speaking, these are not quote-unquote motions of the triangle in the plane because they require you to flip it over out of the plane. So if you're a flatlander, you can't do it. Alright, now the permutation representation corresponding to the symmetry group of the triangle is simply found by the study of the motion of the vertex labels. So let's look at R. R, it takes 1. Where does 1 go? 1 goes to 3. Then where's 3 go? 3 goes to 2. What happens with 2? 2 goes to 1. That's why I write R corresponds to the 1, 3, 2 cycle. R squared. Alright, 1 goes to 2. 2 goes to 3. 3 goes to 1. That's why R squared is the 1, 2, 3 cycle. The flip. Flip. 1 goes to 1. 2 goes to 3. 3 goes to 2. That's a transposition, 2, 3. RF. RF has done what? It has fixed 3 and it's flipped 1 and 2. That's why RF is the 1, 2 cycle. R squared F has fixed 2 and flipped 1 and 3. That's why it's the 1, 3 cycle. And so, in total, the isomorphic copy of the symmetry group of the triangle is this set of permutations on S3. It just so happens that is S3. But on the other hand, the symmetry group of the triangle is the definition, the geometric definition of the dihedral group, D3. And so we've shown that the dihedral group D3 is isomorphic to S3. Woohoo! By picture. Maybe you like that. Maybe you don't. It's up to you. Another group I thought would be fun, and it's kind of a little bit non-exciting, but trapezoid. So here's your trapezoid, your friendly neighborhood trapezoid. And this picture here, I thought about it for a little bit, and realized, well, I got the identity, and pretty much the only thing else I can do is flip it over the axis like that, and that's kind of all she wrote. So the symmetry group's got 2 things in it, and this seems like a rather ridiculous use of S4, but there you go. There's the representation of the symmetry group of the trapezoid inside S4. It's 1 and this transposition. Yay. Obviously the symmetry group of the trapezoid is Z2. Alright, it's the group with 2 elements. I just thought about for a second, what about a circle? If you tried to do this for a circle, maybe like label a point on the circle to try to keep track of what's going on. You could like flip it. You could rotate by angle theta, then the inverse would be rotation by minus theta. That makes sense for any real theta. This is an infinite group. And also the well, the flip is the same as the rotation by pi too. I don't know. Anyway, the symmetry group of a circle is very big, and so I cannot represent it in Sn for finite n. That was, okay, there's an example of what I was mumbling about earlier. Great. Here's another one. And this one is not yet done. So here's what I originally did. I don't know the name of this thing. What do you want to call it? Short Band-Aid? I don't know, whatever that thing is. What do you want to call it? But this thingamajigger-majoo, oh no, I better come up with a better name. We will call this shape, I don't know, what should we call it? So many choices. Call it Zelda. Why not? No, that's too much to say. I better come up with a shorter name and get on with it before the world falls apart here. But we'll call it the Smooshed Rectangle, I guess. All right, so the Smooshed Rectangle obviously allows the identity because it's been symmetrically smooshed. It allows this flip and it allows that flip. And you can actually see that if you make yourself a little demo. So here's the identity. Whee! And here is the flip. So it goes, it's supposed to flippity floppity. So flip on the vertical axis like so, as you can see. The 1 to 2 to 3 to 4. Oh, great. On the other hand, we can start with our initial, and then we do our flip on the horizontal like so. My labels will get upside down, but big deal. You can tell what's going on. So you got your 1, your 4, your 3, your 2. Fine, that's physically reasonable. And then I thought I had some diagonals, but then I was like, what's going on here? I can't make sense of things. And then I realized what the problem was. So if I try to say, okay, well, start like that, and then I'm going to flip over my diagonal. Let's flip over the diagonal. What happens? In other words, I fixed 2 and 4. Oh, no. Clearly, right, D2 of Smooshed Rectangle is not equal to the Smooshed Rectangle. Keep in mind that we're not allowed to say, well, it's still a Smooshed Rectangle, but it's twisted, or it's tilted. Like a symmetry, by our definition, it maps the set of points to the same exact set of points. Now, when you hear people talk about symmetry in general, it can have other more nuanced meanings. So beware, symmetry is much like beauty in the eye of the beholder. Now, likewise, this is not a symmetry, because if you try to think of that, you do not get that again, right? So it's not this bogus. All right. On the other hand, you can calculate that if you do F1 and then F2, you get F21, which is this. In other words, F2, F1 is actually R pi. And so, anyway, I just wanted to study the symmetries of a squished rectangle a little bit. You have a rectangle in your homework, and maybe these don't go away for you guys, right? But anyway, that's how I think about it. There's a geometric aspect to these kind of problems, which means that, you kind of have to look at it and see it when you're done. And if you feel unfulfilled by that, well, okay, maybe you're an algebraist. I don't know. Anyway, thanks, guys. That's it. Oh, man, I still have 12 minutes to blather on. Whatever will I do? I guess I'll go outside and look at the rain pounding down upon the ground. That's what I'm going to go do right now. Yep. That's what I'll do. Anyway, thanks, guys. Have a good weekend.